Welcome to the fourth series of lectures on real analysis. So in this lecture, we would like to discuss how to go from a pre-measure to a measure. Okay, so we are interested in specifically to the following extension problem. So given a pre-measure space X R mu, where R is a ring consisting of subsets of X, we would like to determine if there's a measure and if it is unique, a measure space X sigma gamma in such a way that the sigma algebra sigma contains the ring R and the restriction of the measure gamma on the ring is equal to mu. So these two properties just tells us that gamma, your measure, is an extension of your pre-measure mu. So we would like to extend the domain, which is the ring in this case, into a sigma algebra, which is a sigma. So recall from last time, okay, so if you have a pre-measure nu defined on the semi-ring H, one can extend this to a pre-measure, say mu, on the ring generated by H. Okay. So what you do is basically you apply the property of the ring generated by a semi-ring, that is, any element of the ring can be partitioned as a pairwise disjoint union of elements in the semi-ring. Okay. And then mu will be uh, defined simply by taking the pre-measure of the sets in the partition. With regards to the extension problem, what we would like to find is a sigma algebra that will contain the ring R. In this case, you will have the canonical injection, which is basically the identity map, in such a way that we can define a measure gamma on this sigma algebra. So this lower part here is the extension problem that we are uh, interested in. Okay, so there are two issues that we need to resolve in the extension problem, and that is existence and uniqueness of a measure. Okay, so first let us discuss existence, or uniqueness, I should say. And for uniqueness, we have the following theorem. So suppose that, so A, I have a collection script E of subsets of X that is closed under intersections. Okay, example of this would be an algebra. And then B, E is the generator of the sigma algebra sigma. So in other words, the sigma algebra generated by E or script E is sigma. And part C, one can find a countable sequence of elements in the generator E, wherein this E sub n increases to X. Okay. And just to recall, what does this mean? This means that En is a subset of En plus 1, and X is the union of the E sub n's. Okay. Now, if you have two measures, say mu1 and mu2 on sigma, satisfying the following properties. So D, the two measures coincide on the generator. In other words, the values of the measures are the same for all elements in the generator script E. And that part E, the measures for the sequence in C, the E sub n's are finite. Okay. So for instance, C and E are satisfied if the pre-measure or the measure space associated with mu1 and mu2 are sigma finite. Okay, so assuming all these properties A to E, then we can say that the measures coincide. So this is some sort of a uniqueness. So this theorem tells us that if you have two measures and they coincide, the values coincide on the generator, and your, let's say, your measure spaces are sigma finite, then the measures are the same. So that is some sort of uniqueness. So if they are equal on the generator, then they are equal on the sigma algebra, loosely speaking. Okay, so let us look at the proof of this theorem. So the goal here, so we need to show that, so here we have two functions, mu1 and mu2, defined on the same domain, and they have the same codomain, that is the set of non-negative extended real numbers. To show that the two functions are equal, it is enough to show that the values are the same. So for any set in the domain, in this case, the sigma algebra. So this is what we want to show. To show this, let us define a collection script D. So we collect all elements of the sigma algebra where the two measures coincide. Okay. So just take all elements of the sigma algebra wherein this is valid. Okay. Now, with this, we claim that D is in fact equal to sigma. And if this is the case, if D is equal to sigma, then this is in fact the one that we wanted to show. Why? Because if this sigma, this means that every element in D, in other words, every element in sigma satisfy this property, which is our goal here. Okay. Now, to show that D is equal to sigma, we will show that. So in the following, we would like to show that D is a Dinkian system. And how does this imply our claim? Now, to see this, let's start with this fact that the generator of sigma is E, and that is, if we go back to the set of assumptions, that is part B. Now, the sigma algebra generated by E is the same as the Dinkian system generated by E. This comes from the fact that E is closed under intersections, and recall from last time, we have shown that if you have a collection that is closed under intersections, then the sigma algebra and the Dinkian system generated by that collection coincides. Now, the Dinkian system, okay, D, if that would be the case, contains E, okay, and why is that? That is due to part D, okay. According to part D, mu1 and mu2 coincides with the generator. So therefore, all elements in the generator satisfy this property. Hence, they should be in D. So D is a Dinkian system containing E. So let us emphasize that one. So according to D, the Dynkin system contains the generator. Okay, since delta E is the smallest Dynkin system containing E, then this delta E must be a subset of this Dynkin system capital or script D. Okay. Now, according to the definition of D, so look at this. Elements of D are taken from a sigma. So by definition of D, D is contained in sigma. So we started on the left with sigma and we end with on the right with sigma. So in other words, uh, all sets here are equal. So in particular, if all sets are equal, then you have what? D equal to sigma, which is our claim. So you can just concentrate on these three parts here. Okay. So sigma is a subset of D, but D is a subset of sigma. So therefore, D is equal to sigma, which is our claim. Okay. So to summarize, we would like to show that all values of mu1 and mu2 are the same on the sigma algebra. We introduce a Dynkin system, which is the collection of all elements in the sigma algebra satisfying this property. If we can show that D is equal to sigma, and this is done by showing that D is a Dynkin system, then all elements of sigma satisfy this property here. Okay. So therefore, it remains to show that D is a Dynkin system. So let us establish that one. So the first property, we would like to show that X is in D. Okay. So let's start with the measure of X with respect to mu1. Now, recall that E sub n increases to X. Okay. So therefore, the limit of the measures of E sub n with respect to mu1 is equal to mu of X. This comes from the fact that we have C. So going back to the assumption here, okay. So En increases with X and continuity, and apply continuity from below. Okay, I recall that we have shown last time that a pre-measure is continuous from below, a pre-measure defined on the ring. Okay, so in particular, a measure on a sigma algebra, since a measure is a pre-measure and a sigma algebra is a ring, this implies that measures are also continuous from below. Okay, now mu1 is equal to mu2. This is according to what? Property D. Since the sets E sub n, okay, and also a property C, okay. So look at here, since E sub n is are elements of the script E, and all elements of script E have the same measure with respect to mu1 and mu2, then in particular, taking E to be E sub n in D, you have equality of mu1 and mu2. And of course, these two are the same after taking the limit. Okay, so that's this part, this equation here. Next, applying again C and continuity from below. So this would be this part here. Okay. we get mu2 equal to should AX. Okay, so therefore, take note that X is always in the sigma algebra. Okay, so X is in sigma. They have the measure with respect to mu1 and mu2 are the same according to the definition of D. X is in D. So that's the first property. The next part is we wish to show that D is closed under complementation. Okay, so for this, we would like to establish or to add a condition. To see that later, let's start first with an A element of D. Okay, then according to the definition of D, this means that A is in sigma, and so the complement, which is X minus A, the set difference of X and A is also in sigma. Okay, so the end, you would like to see whether the uh, measure of the complement with respect to mu1 is the same as the measure of the complement with respect to mu2. Okay, so with that, let us apply the fact that the complement is, as I said, X minus A. Now, if it is possible to write down this as the difference, okay, well, this is the case because A is a subset of X, and provided that mu1 of A is finite. Okay. The problem here is that we do not have a guarantee that this is indeed a finite value. So for this part, we need to separate. So the first step is that we would like to establish or assume that mu1 and as well as mu2 are finite. So this is our first step. So according to D2, we end up with something that we would like to satisfy. In other words, this one. Okay. But as I said, there's no guarantee that this is valid. So therefore, let us assume as a first step that mu1 is finite. Okay. Now, since A is in D, this implies that, okay, so let us emphasize that one, if because A is in D, the measure of A with respect to mu1 is the same as mu2A. So let us just copy this one. So here we establish the equality this because A is in D. Okay. Now, according to step 2, I can replace, or the first property, I can replace this by mu2. Okay, so that's D1 and A in D. Because in D1, we already know that mu1 of X is the same as mu2 of X. Okay. And we can combine this into a single measure. So this is mu2 X minus A. Again, as we say, this is valid whenever mu2 is finite. Well, that is what we have mentioned a while ago. In this step, we assume that mu1 and mu2 are finite. Okay, and therefore, mu2 is, this one is equal to mu2 of the complement. So we have shown that the complement of A has the same measure with respect to mu1 and mu2, hence the complement is in D. This establishes the closure of D with respect to complementation. And finally, let us show that it is closed under pairwise disjoint countable unions. For that, let us take a countable sequence of elements in D, say A sub n, and it is pairwise disjoint. Okay, according to the definition of D, all of these sets are in the sigma algebra. So AN is in sigma for all n. Hence, the countable union is also in the sigma algebra. Now, it remains to establish that the measure of this union is the same as that with mu1 and mu2. Okay, so let us first look at the measure with respect to mu1 of the pairwise disjoint union. Okay. Now, being a pairwise disjoint union and mu1 is a measure, therefore it is sigma additive. So the measure of the pairwise disjoint countable union is the sum of the measures. So here, you see the importance of being a pairwise disjoint collection. Otherwise, we would not have this equality here. Now, since AN is in D, okay, there should be a subscript 1 here. So the measure mu1 AN is the same as the measure mu2 AN. So each terms coincide, therefore the series also coincide. And applying also the sigma additivity of mu2, then the last or the second series is equal to the measure mu2 of the union. Therefore, the union is in sigma and the measure coincide with respect to mu1 and mu2. Hence, the union of the A sub n's is also in D. So, therefore, we have established that D is indeed a Dynkin system. And according to the statements at the beginning of the proof, I'm referring to this one here. Okay. Therefore, the theorem is valid first in the case where mu1 and mu2 are finite. Okay. Now, what if we remove this condition? In other words, what if mu1 and mu2 can be infinite? So that would be the second step. So here we will now discuss the general case. So this means that mu1 can be infinite at some set, or mu2 can be infinite at some set. Well, the idea here is to consider restriction measure spaces. So let us consider the following. Restriction measure spaces, say X sigma, and then we restrict the measure mu1 and mu2. So say mu sub I is either 1 or 2. We restrict that to the E sub n's. These E sub n's, take note, are increasing and tends to X. And here n is a positive integer. Okay. Now take note that, okay, if we take the measure of x, let's say with respect to this restriction measure, mu1 e sub n. By the way, how is the restriction measure defined? So this is just mu1, and then let's say x intersection e sub n. Okay, this is basically the definition of the restriction measure. So to take the measure of the set, you just take the measure of the set intersection with uh, whether with this C sub set E sub n. Okay, so that's the definition. Of course, E sub n is a subset of X, therefore the intersection would be the smaller set, in this case E sub n. And we know already that mu1 En is the same as mu2 En. And let us see that one. Where's that? So going back here, I think D and C. Just to remind ourselves, this is D and C. And again, going back, so this is the restriction measure of, or let's say this is mu2 x intersection E sub n. Hence, this is the restriction measure mu2 En of x. Okay. Take note that according to this is finite. And this is according to D, or I should say C and E. Since all E sub n's, okay, all E sub n's are in the generator, and the statement that E means that all mu1 En or mu2 En are finite. Okay, so I think it is enough to mention E in this case. So based on this calculation, these restriction measure spaces are finite. Okay, because if the measure of the whole set is finite, in this case x, then you just apply monotonicity, and that would imply that all values of mu1 En and also mu2 En are finite. Okay, so we are now reducing this first step, step 1. Okay, so we would like to verify, so that mu1 En and mu2 En, these are now finite measure spaces, or measures, I should say. They satisfy, okay, the two conditions of the theorem. So therefore, we need to verify if D and E are satisfied. Okay, so to show this, let's start with D. So for all E in script E, and for all N, by the way, what is D? Going back to the statement of the theorem, so we would like to verify that the two restriction measures coincide with the generator script E. So as a first step, let us look at elements E of the script E and indices N, okay? Then mu1 En. Okay, by definition, this is mu1 E intersection En. Now, take note that this intersection is in script E because E and E sub n are both in E by A. Take note that our generator is closed under intersections. Okay, and therefore, this is equal to, okay, and this is what? The property D, but what is D here? D for mu1 and mu2. So the measure mu1 and mu2 coincide on the generator. Since the intersection is an element of the generator, therefore their measures coincide. So that's easy. So this is by definition mu2 En of E. Hence, property D. So by this D here, so to emphasize D, but what is D? D for the restriction measures mu1 En and mu2 En. Okay, so D is satisfied for mu1 En and mu2 En. The second part is E, okay, for mu1 En and mu2 En. Well, this follow immediately since what? The restriction measures are finite. Okay, since mu En is finite for I equal to 1 or 2, then this implies immediately that mu En, well, let us use a different subscript here, M, E sub M, is finite for any M, and I 1 and 2. So therefore, E is also satisfied for what? For the case of the restriction measures. So therefore, from step 1, this guarantees that, well, let us emphasize here, step 1 for the restriction measures, mu1 En and mu2 En, we are guaranteed that these two restriction measures coincide with the sigma algebra. So in other words, this equation holds for any element in the sigma algebra and for any positive integer n. Okay. And from this, we can now, so therefore, for any, and for all A in sigma, okay, take note that what? Since E sub n increases to x, we are also guaranteed that the intersection A intersection n increases to A intersection x, and that is A. Hence, applying continuity from below for the measures, we would have the following. Okay, so mu1 of A, continuity of the measure means that measure mu1, this means that since A intersection En increases to A, so taking the limit of the measure would be the measure of the limit. In this case, the limit is A. Okay, so this is nothing but the limit of the restriction measure by definition. Okay, now if I will, let's say, let us name this as a star. If we apply this star in the following equation, take note that mu1 is equal to mu2 En of A. And again, applying the continuity from below now for the measure mu2, this is now mu2A. Hence, mu1 of A is equal to mu2 of A for all A in sigma, showing that the measure coincide. And that's the theorem that we would like to establish. So to recall, as a review, let us look at the definition or the statement of the theorem. So suppose that you have a generator E of the sigma algebra that is closed under intersections, and you can find a sequence of elements E sub n in the generator that will increase to the set X if you have two measures that coincide on the generator, and these two measures are finite with respect to the sequence, then we can say that mu1 is the same as mu2. So that is the uniqueness theorem. The existence will be established in the next lecture.